In this video, we're going to continue working on our example for our mobile phone network. So remember, here was our diagram. Here's sort of our diagram showing our amplifiers and losses. And ultimately what we were trying to find is the maximum allowable value for our space loss, this L sub S, given specifications for all of these other components in the system. And so as we had said when we were first writing this diagram, what we're going to be interested then is the signal to noise ratio at the receiver. So remember, our P sub SR is our power of the source, or the power of the signal at the receiver, and our P sub NR is the power of the noise at the receiver. So let's just refresh ourselves briefly on our specifications. So again, we're looking for our maximum acceptable space loss. We have our transmitter power, our transmitter antenna specifications, our frequency, our receiver antenna specs, receiver amplifier specs, receiver cabling specs, and then ultimately we said our receiver needs a -7 dB signal to noise ratio or higher in a bandwidth of 360 kHz in order to operate. So what we're trying to meet then is we want to look closer at this signal to noise ratio at the receiver. And so we know that is equal to the power of the signal at the receiver divided by the power of the noise at the receiver. So to be consistent with my notes, I'm going to label this as equation 1. And so what we're going to do then is we want to get equations for our P sub SR and our P sub NR. So let's first start with the power of the source at the receiver. So the power of the power of the signal at the receiver. So our power of the signal at the receiver is simply going to be whatever we initially had on our transmitting side. Let me get rid of some of this highlighting for clarity. So whatever we had at our transmitting side multiplied by any of the gains. So we have antenna gains, our amplifier gain, and then divided by any of the losses. So in this case, we see we have losses for our space loss and through our cabling here. So this one is going to be relatively simple. We can just write that the power of the signal at our receiver is equal to whatever was transmitted multiplied by all of the gains. So we have gain for our transmitter amplifier, gain for our receiving amplifier, transmitting antenna and receiving antenna, and then we have our low noise amplifier, which has G amp. And just to be clear, with later on, I'm going to specify that, so that's going to be G amp. We're going to need to turn that into a linear scale. And then we're dividing by all of our losses. So we're dividing by our space loss, L sub S, and our cabling loss, L sub C. So this is going to be equation 2. So now we need an equation for our noise at the receiver. So we want to look at the power of our noise at the receiver, and essentially what we're going to do is we're going to see this equation is very similar to the one where we were considering effective input temperature for a system. So what we're going to do is we're going to have our Boltzmann constant K sub B multiplied by the bandwidth, and then we're going to have different components multiplied by gains and divided by losses. So for instance, our temperature of our receiving antenna, as well as the temperature of our amplifier, and these are effective input temperatures, are going to be multiplied by G amp and divided by the loss in the cable LC. And again, we're essentially treating that cable as if it has a gain of 1 over LC. So it's attenuating the signal. We then have plus, we also have this separate term, which is going to be 1 divided by LC, so multiplied by this gain of the cable, times TC. But what I'm going to do is I'm going to substitute for TC. So remember, we had an equation for TC that said it was TA times 1 minus 1 over LC. So let me just put here that this was RT sub C. And so again, to be consistent with the notes, let's call this equation 3. And so if that third equation was a little confusing, if you're looking at the lecture notes in Canvas, you can look on page 6-13 equation 1, and this should be the same form as that equation. So what we're going to do now, of course, is we're going to take equations 2 and 3, and we're just going to substitute it into this simple equation 1 to get our signal-to-noise ratio. So doing that, what we have is that our signal-to-noise ratio at our receiver is equal to, so in our denominator, we have loss of our space loss from our cable, then we have this KB times our bandwidth, so we're going to have this whole piece of n term up here. And then in parentheses, we have our TRA, receiving antenna, plus T amp, all of that multiplied by G amp divided by LC, plus our TA over LC times 1 minus 1 over LC. Okay, and then in the numerator, we're just going to have those other terms from our equation 2. So that's going to be PT. We're going to have PT, power of our transmitted signal, the gains of our two antennas, GTA, GRA, and the gain of our preamplifier, G amp. So, of course, what we're looking for, though, is we're trying to solve for the maximum allowable space loss. So we can just rearrange this a little bit. So let me just copy, paste, and rearrange. So what we're looking for is we want to change these two. So I'm going to move my LS over here. And again, because we're trying to solve for LS max, that's going to correspond to a signal-to-noise ratio minimum. And so let's call this equation 4. And this is the equation that we're going to need to use to solve for this LS max. But before we go about plugging in values and solving for that, let's note a couple of things here. If we look at any of these terms in the numerator, so we have our transmission power, our gains for our antennas, or our gain for our amplifier, increasing any of these terms in the numerator is going to increase maximum allowable loss. So let me just say numerator terms increasing means we have LS max also increasing, of course. What we can also see is some of these terms in the denominator, our minimum signal to noise ratio, our loss in the cabling, our bandwidth, or any of these noise temperatures. If we are increasing any of these, then we're decreasing our maximum distance or our maximum loss. So let's just say if we're increasing, for instance, our minimum allowable signal to noise ratio, so we're saying it has to have a better signal to noise ratio, our cabling loss, our bandwidth, any of our effective input temperatures, then what that corresponds to is a decrease in our LS max. The one other thing that we can look at is we see this ratio here, and we have this LC in a couple places, but we can see that as that G amp gets larger, the effects of LC in that particular term are going to be becoming less significant. So sort of two reasons why we want to have that G amp be a little larger. Okay, so now we're almost ready to plug this in, but if we go back to our known values or our given values, we have a couple of them that are given in decibels. And to plug into here, we want to have linear versions of that. So we want linear, so non-dB values to plug into that equation. And so we're going to need linear values for our G amp, our signal to noise ratio minimum, our T amp, and our LC. And so again, the reason for that is if we go back and look at our given values, all of these were given in terms of decibels. So not too difficult. We're just going to have to do some math to convert that to our linear scale. So let's start by looking at our amplifier. So for our amplifier, we were told that our gain of our amplifier in decibels is equal to 15 dB. And so we know that is equal to, by definition, 10 log of G amp, our linear G amp. And so note, I'm using 10 in my definition of dB because we're dealing with powers. So let me just note here that we are dealing with powers. If we were dealing with voltages or currents, that would be a 20 instead of a 10. Okay, so if we solve this then for G amp, we can just say that our G amp is equal to 10 to the power of 15 over 10, and that comes out to be approximately 31.623. So our T amp, so this was our gain of our amplifier. We also want our, so let's just mark that out. We've covered that. So our T amp we can get from our noise figure. So remember we had an equation to get noise figure from a given effective input temperature, but of course we can rearrange that and we can say that the T amp is going to be equal to the ambient temperature, which is 290 Kelvin, and then we multiply that by 10 to the power of our noise figure in decibels divided by 10 minus 1. And so if we plug all of that in, we get approximately 169.619 Kelvin. So here we found the gain of our amplifier and our effective input temperature of our amplifier. So let's now look at the minimum signal to noise ratio at our receiver. So looking at our receiver, we have that our SNR min in dB was equal to -7 dB. Not sure what happened there, -7 dB. And so of course, using the similar relation we had above, we can say this is 10 log of our linear signal to noise ratio min. So that linear signal to noise ratio is just going to be equal to 10 to the -7 over 10. Plugging that in, we get that that's about 0.200. And so that's pretty crazy to think about. What this means is that the power can go as low, the power of our signal can go as low as 1/5 of the power in our noise. So our noise can actually be stronger than our signal, but this receiver is still able to sort of pull out that signal undamaged. Okay, so we've taken care of this signal to noise ratio min. We got that that's about 0.2. And then the last thing we want to look at is the loss in our cabling. And so remember, for this coaxial cable, we were told that the LC in dB was equal to 3 decibels. So 3 decibels, which again is just going to be 10. It's just not cooperating today. So 10 log of our linear LC. So we can say our linear LC is equal to 10 to the power of 3 over 10, which is approximately equal to 1.995. And so let's make this a little simpler and just call that 2. Okay, so now that we have all of these, we're ready to go back and plug into our equation 4. So we're essentially just going to take this equation. So let's actually just copy this and bring this down here so we can kind of have it for reference as we're plugging in everything. So here's our LS max, which is what we're solving for. And so we have our LS max. So LS max is equal to, so now our power transmitted, we said was 250 milliwatts, so that's going to be 0.25 watts. Gain of our transmitter antenna was 1, gain of our receiver antenna was 63, and gain of our amplifier was 31.6, roughly. Our minimum signal to noise ratio after we converted it to a linear scale we found was 0.2. Our LC we approximated as 2. It was a little less than that, but close enough. Our Boltzmann constant, remember, is 1.38 times 10 to the minus 23rd. and that's joules per Kelvin. We then have our bandwidth that was given as 360 times 10 to the third, so 360 kilohertz. And then plugging in for our temperatures, we have 290 K for our antenna temperature, plus the effective input temperature of our amplifier, which was 169.6, multiplied by the gain of our amplifier, so 31.6 in the numerator, divided by the loss of our cabling, which was 2, plus, now we have our TA over LC, so our ambient temperature of our cabling, which was 290, divided by LC, which was 2, and then times 1 minus 1 over our LC, which again was 2. Okay, so plugging all of that into our calculator, what we get is our LS max, our maximum allowable space loss, is approximately equal to 3.415 times 10 to the 16th. And so this is going to be a dimensionless value. So oftentimes though, we'll express this in terms of decibels. So if we do 10 10 log base 10 of that value, we can get our LS max in dB. And we find that that is approximately 165.3 dB, which is a fairly large amount of space loss that we can allow and still have our system to operate properly. So what I said earlier is we can come back and we can use our sort of general, or rather our specific case for free space loss, and we can compare it to this maximum space loss for a given distance. So let's consider our free space loss for this signal over a distance of, let's say, 1 kilometer. So let's consider our free space loss. And so remember, we have a 2.4 gigahertz signal over distance of 1 kilometer. So of course 1 kilometer is 1,000 meters. So if we go back to that simple equation we had earlier for our space loss in free space, we said that's equal to, in the numerator we have 4 pi times our distance in meters, so 1,000, divided by, and now in the denominator we have, if it's free space, our signal is traveling at the speed of light, so we have 3 times 10 to the 8th meters per second, and then our frequency, which is 2.4 times 10 to the 9th per second, square all of that, and what we get is approximately 1.01 times 10 to the 10th. Well, if we convert that to dB, so we do 10 log base 10 of that, what we get is our L in free space in decibels is equal to approximately 100 dB. And so using that as a point of comparison here, is we can say that if we were in free space, then we could be further than 1 kilometer away and still be meeting this maximum, still be within our bounds of this maximum allowable loss. Or alternatively, again, we could say in a real system, we're going to have interference from buildings, trees, various things like that. So maybe this system up here is for operating more on the range of 1 kilometer, but we have all of this interference, which is going to increase our loss above this simplistic case of just the signal traveling through free space.